Hello everyone. Today I'm going to present the oreboot status report. First, I'm going to go over what oreboot is, how it's related to coreboot, some of the firmware challenges we've encountered, the design principles we've created for oreboot, some challenges we had with Rust, which is the programming language we decided to use for oreboot, and some of the target platforms we have implemented oreboot for. And here are some of the oreboot developers, myself, Prachi, Gon. Also not here is Titus and Ron Minnick. All right, so to begin, what is oreboot? So over the years, there's been many open source firmware projects. This is kind of an incomplete history. So you can see this coreboot, Slim bootloader, Linux boot, U-boot, UBMC. So a lot of different projects. But what they all have in common is they're all written in C. They're all written in mostly C. Maybe there's some assembly. I think coreboot also has some ADA, I believe, as well. But for a lot of these projects, it's mainly C. And for Linux boot, there's some Go in the user mode. But there's always some C, which makes it, to some extent, a bit unsafe, because you could have things like out-of-bounds errors or unchecked dangling pointers and double freeze and issues like that, which you encounter in the C programming language. So oreboot aims to address that. So it's kind of a pun. It's coreboot without C, oreboot. And it's also a bunch more. So it is a fork of coreboot. It's also open source and has to be under GPL v2 for that reason. It's completely in Rust. There's a bit of assembly, like for the very early initialization. For example, setting up the stack pointer for the first time, or jumping from real mode into protected mode into long mode. But after the initial piece of assembly, it's all in Rust. And a big aim of oreboot is to jump to an operating system as quickly as possible. So it doesn't have any, or it doesn't have many drivers, like it doesn't have a disk driver or a networking driver or USB stack. The aim is to use something such as Linux boot, which already has well-developed and safe drivers for those functionalities, and to lean on Linux boot rather than implementing it all in oreboot. So the idea is we jump to the operating system as quickly as possible, and we let Linux boot do the rest. And we have some policies surrounding closed source blobs, which we think are a bit more strict than coreboot. We're aiming at not allowing every possible implementation which has closed source blobs. I'll talk a bit more about that later. And there's a few ports available. So I believe you have an ARM port, RISC-V port, an x86 port, some ports for QEMU as well. Okay, so here are a few of the design principles for oreboot. So like I mentioned, we jump to Linux boot as quickly as possible. But in the early phases, we have a bit of assembly. So setting up the cache as RAM, setting up SRAM. And there's an initial print, which is welcome to oreboot, which is in raw assembly. Once we get to the ROM stage, everything is in Rust. And there's, at this point, on many systems, it has very little memory to deal with. Probably somewhere between 30 kilobytes and 8 megabytes, which is the cache's RAM. So in this stage, you initialize RAM, and then pretty much as soon as RAM is initialized, we flip over to loading the payload in what we call the payloader stage. So the current payload we support now is Linux, and then we let Linux kexec into another kernel or do some work such as a netboot. All right, so this is a bit of Rust code. If you're not familiar with Rust, it's very similar to, or the syntax looks reminiscent of C or C++. So you'll see here we have what's called a trait, which is very similar to an interface. And you see this trait has 4 functions, an init, pread, prewrite, and shutdown. So these are the 4 functions you have to implement in order to write a driver. And you see the reason we use pread and prewrite rather than just read and write is drivers don't keep track of a cursor. It's the user of the driver, the client of the driver, keeps track of the cursor. And this allows drivers to be thread safe, right? So you could have multiple clients of a single driver, and since each one keeps track of their cursor, there won't be any memory erasers. All right, and you can see a few other neat properties of these drivers, but I'll move on. All right, so these are a few types of drivers that we have in oreboot. So we have physical drivers. So for example, we have a memory driver, which lets you read and write to physical memory. We have a few serial drivers, so the PL011 that's popular on ARM systems. The other types of serial drivers are popular on x86. We have an MMU for controlling the state of the MMU. We also have a SPI driver for Sci5 because you can't, only 16 megabytes of the SPI part is memory mapped. You need some special control logic to access the rest of the SPI device. Finally, we have what we call virtual drivers. So these don't control physical pieces of hardware. Rather, they're used to combine other drivers in useful ways. So for example, we have a slice reader. So if you want to read from a specific region of memory, you use a slice reader. And then we also have the union driver, which I'll describe on the next page. So the union driver operates on multiple drivers, and typically we use it for multiple serial drivers, such as UARTs. And you set up the union drivers as shown here. You pass in a list of drivers, and every write operation, actually, sorry, I should say a slice of drivers, and every write operation to the union driver writes to each one of those drivers in the slice. So for example, when we write welcome to oreboot, it gets written 5 times to all these UART drivers. So it's fairly convenient. And in actual setups, we often write to a UART driver and to a console log at the same time, which is a memory-based driver. So this makes it very easy to add and remove drivers. You just edit the code to configure it. And you also get, in Rust, a benefit of Rust is you get printf for free. You'll see in lots of C programs, they've re-implemented printf. For example, Coreboot has its own implementation of printf. Linux has an implementation of printf. EDK2 has an implementation of printf. Pretty much every single C program out there has its own implementation. But Rust is very convenient in that printf is part of the standard library. More specifically, a printf implementation, which is independent of the operating system, so doesn't perform any syscalls, as part of the standard library. All right, so this is how we define the flash layout inside of oreboot. So we do something kind of similar to CBFS. However, we call it DTFS. So the metadata is in a device tree syntax, and this is convenient in that the Linux kernel already has a means to parse the device tree. So we simply pass the device tree, which is the device tree file system, as a node to the Linux kernel, and then you can access it through sys/firmware/device tree. And then you can see, you can also include files inside of it. For example, if you want your Linux kernel to display a splash screen during boot, that splash screen could be part of this DTFS. And then Linux would be able to read it from sys/firmware/dt/ the path to it. So it's rather convenient. So it could be used for metadata, splash screens, etc. And here's an example of the flash layout that we used for I believe this is the RISC-V, the Sci5 Hi5 chip. So you'll see there's a boot blob at the beginning, followed by the fixed DTFS, which is this metadata for the device tree file system, followed by 2 NVRAM sections, which oreboot currently doesn't support yet, followed by the ROM payload, followed by the RAM payload. And there's an A and a B partition. All right, so now I'm going to go over some challenges we had with REST specifically. So the first one is no dynamic allocation. So we're using what is called no STD in REST, so no standard library, which means a lot of the functionality of the standard library is missing, and instead you use REST's core library. So by default, there's no dynamic memory allocator. And so far, we've gotten away with only using stack-based allocation. And in fact, we believe this has led to a better design, only having stack-based allocation. It means whenever you call a function, everything has to be passed into this function via the stack. You can't access global memory, and you can't access pointers to information outside of the stack. So the reason this has led to better design is we're able to unit test these functions easier. It's very easy to mock out since everything is passed into the stack. It's not allocating stuff on the heap. It's been fairly easy to unit test these. And it also allows us to guarantee a maximum stack size. So at compile time, we can say the stack size will be no more than X. The LLVM compiler has a utility which tells you how much stack each function uses, or that function, all the functions it calls uses. That's called the call stack. So then we can guarantee that the functions will all execute within SRAM, which has a fairly limited size on some processors. The other challenge we're running into, well, not necessarily a challenge, but something that we want to improve in the firmware space is boot time. We want to enable multiple threads, not necessarily threads, but they're called coroutines in the firmware, so you could perform multiple tasks at the same time. So for example, UART is very slow, and oftentimes in firmware, it has disabled interrupts, so we have polling UART. So measuring it, you could easily find the number of UART prints adds up to some very large number, like maybe you have thousands and thousands of characters being printed UART, and it adds up to a second. But what you can do is, it's difficult to enable interrupts in firmware because, how do you put this? Because it's very challenging to do well and get right. Even in the Linux kernel, there's a lot of complexity involved. And we also don't want oreboot to become a kernel in its own right. We want it to be very, very simple. So instead, we want to do non-preemptive threading. Essentially, each thread it won't block indefinitely. It will resume control to other threads, and REST has a mechanism for this called async await. But we still have to do a fair bit more research into this, and this is an area where we could use some help. So the next thing I want to bring up is the targets and the ports that oreboot currently runs on. So we have the QEMU system ARM. This is QEMU, and we ran it with the virt machine. And this was fairly easy to set up. We set this up in the summer of 2019, and it only took a couple of days. Since it was fairly basic, there's no memory that has to be initialized. You essentially dump the REST program into memory. QEMU runs it, and it's fairly easy to implement the PL011 UART, which conforms to the way QEMU works. So this was all fairly easy, and I can show you the quick demo of it running. First, changing to the QEMU mainboard for ARM. And then I type in this command, the cargo make run, which first builds for the ARM QEMU platform, and then it runs it inside of QEMU. And this all went by quite quickly, so I'll step through it one step at a time. All right, so this is building. This is it dumping the device tree, which was provided by QEMU. And you'll see here it's booting Linux. I think this is just a debug print. So it's fairly quick. It doesn't have to do much work. Essentially, this passes the device tree that QEMU provided to it directly into Linux. And that's pretty much it. All right, so here's a demo of the Sci5 Hi5 processor running inside of QEMU. And if we scroll back up, we can see with a single command, cargo make-p release run, this builds oreboot as well as runs inside of QEMU. So you see all these first steps here, was building oreboot, and then it boots so quickly that it's hard to tell. But this is it running inside of QEMU, and you can see tested DDR starting to fill data, read data, passes, loading the payload. I think this was some debug print, and then this is the Linux kernel, and you can see it's running the Linux kernel in M mode. This was an old demo because you can see it kernel panicked before reaching user mode, but the kernel boots up until the point of reaching user mode and loading the init RMFS. All right, and then that was the first approach for running oreboot on the Hi5 Unleashed. The next thing we did was using OpenSVI in order to run Linux in S mode as intended. All right, and the next platform was the OpenTitan Earl Grey. So this is a very embedded platform. It's not Linux capable at all. It's missing things like an MMU, and it's also very low memory. So you wouldn't be able to run Linux on this. So OpenTitan is an open source designed for root of trust. And you could find it here at this. It's a completely open source silicon design, which is pretty unique. And you can find all the source code for it at this GitHub link. So there's no ASIC available yet. So all of our work was done on either QEMU or in Verilator, which is an emulator for the FPGA, or directly in the FPGA. So our current work is getting oreboot to boot the Talk kernel, which is a kernel also written in Rest. So today, what we've got into is we're able to boot oreboot and perform some prints and read memory and a few basic tasks, but we're not able to completely load a payload on OpenTitan yet. And I also recommend you see this talk, Enabling OpenTitan with FPGA and oreboot, by Sheng at the OCP Global Summit earlier this year, where he discusses the OpenTitan port in more detail. All right, and here's the code structure for the OpenTitan. And this is actually similar to a lot of our ports. So at the root, we have the main board, which is the project which gets built. And it in turn builds the SoC, the system on a chip, which contains an import for the CPU, which contains an import for the architecture. So this lets us reuse multiple architectures between different main boards. So for example, we could use the same CPU on two separate main boards, the same SoC on two separate main boards. As well as you have the physical devices, the virtual devices, etc. All right, so here's the exciting part, the oreboot ground rules for x86. So before we started on x86, we were saying that oreboot will never contain any closed source blobs or support any firmware which requires closed source blobs. However, unfortunately, we found that a bit too limiting because it meant we would never be able to support x86. So we loosen the requirements a bit with these ground rules. You could read them in more detail, but I'll go over a few of the important ones. So the blobs must be redistributable and are ideally available on GitHub. So for example, this would include FSP, as well as number 6. So any compromises to the language safety features of Rest must be explicitly stated. So for example, if a callback or a function that you call inside of the blob returns a string pointer, there's no guarantee that that string pointer points to valid memory. because that pointer has originated from some place which isn't rest code. So at compile time, we can't guarantee that it's going to be a valid pointer. So that has to be clearly stated. All right, so for FSP on oreboot, the first port we're looking into is the up extreme board. And this uses the FSP coffee lake, which is an FSP 2.0 binary. And this blob is redistributable and downloadable from GitHub. And it's very similar. So what we're looking into is very similar to how you would use coreboot in FSP. It's just using REST. So we'd be using API mode. And we'd also be doing this in 32-bit. So oreboot will be compiled for 64-bit. But when we jump into the FSP binary, according to the API mode spec, you have to drop down to 32 bits in order for it to work. Then we're also going to implement the handoff blocks in oreboot as well as the user-provided data in order to pass the information back and forth. So here's a quick overview of API mode. So there's 3 stages of FSP. There's FSPT, FSPM, and FSPS, which initialize the temporary memory, the memory, and the silicon respectively. So we find that the FSPT is optional. We could initialize the cache's RAM directly inside of oreboot in open source. Essentially, it has to be assembly code. But then FSPM and FSPS, we figure are required to initialize memory and the silicon. It's impossible to implement these in open source since we don't have enough documentation and the IP is fairly restricted. It's very difficult to get access to that IP. So what we've done, in order to create the API to interact with FSP, we've looked at the headers of FSP, and we've used a tool called bindgen, which converts these headers from C code into REST code. So I could give you a demo of the documentation that that bindgen generated for us for oreboot. All right, here we go. So all this was generated automatically. It's the data structures necessary for communicating with FSP. So in particular, some of the more useful ones are the FSPM. And you can see here, sorry, not this one, the UPD. Oh yeah, the FSPM config. And you can see here why we didn't want to manually type all this in, since this data structure is quite long. The bindgen did some very useful work for us in converting the C header file into REST. And it's fairly accurate as far as we can tell. It has the correct size of the final struct, as well as all the fields that we expected. And you can see the source code that was generated here. It's quite long, and it contains all those fields. All right, so the next step is filling in this user-provided data structure to pass to the FSP. And we don't have a great way of doing this right now. It was designed for sort of an EDK2 model. It's a special file format with the default values, which it's intended to be used with the EDK2 build system. So the approach we're going to take is we're going to run slimboot on the up extreme with the Coffee Lake FSP. So this already works. They have great documentation in order to run this. The next step is we'll run oreboot in QEMU with the QEMU FSP. So the QEMU FSP is, in fact, it's open source, and you can find it inside of the Slim Bootloader project. All right, so these are the first 2 steps. And then we're going to use step 3 in order to extract a valid UPD for this system. So we're going to use UTK, which lets us swap out the FSP. We're going to use UTK to inject the QEMU FSP into the Coffee Lake image built with Slim Bootloader. So what this allows us to do is to add a hex dump into the QEMU FSP, which dumps the UPD data structure which the lim bootloader passed in the UPD. And then we're going to take this hex dump and place it inside of oreboot so that oreboot will pass the same UPD in to the real FSP. So we've essentially tricked the system into believing it's running the real FSP using the UPD that the slim booter passed in. It's kind of a tricky system, but we think this will generalize to not just the up extreme, but to other platforms in order to get a valid UPD for other platforms as well. And there's a few more work. So after we do this, we expect the FSPM to initialize memory correctly, but then there's more steps such as passing the HOBs returned from the FSP, and then more work in generating the ACPI tables, etc. All right. So we're nearing the end of the talk. So if you want to join the discussion, follow the oreboot channel on Slack. It's free to join. You could find all the source code on GitHub. Please feel free to contribute. We have some great contributors. There's also a lot of help wanted in improving the CI system, implementing more drivers such as a SPY driver. A lot of work has to be done in terms of security in vboot. Not much has been looked into in terms of verifying the boot process. Pretty much none, but Rest has some great crypto libraries if anyone wants to look into that. Finally, there's a lot more work, as I explained, into improving the x86 port of oreboot. All right, so thank you everyone so much. I guess we should start the Q&A now.